welcome you to the Bradford seminar today, and to welcome Dr. Jing Meng here as our guest speaker. She's a professor at the Bartlett School of Sustainable Construction at the University College London, and a fellow of the Cambridge Center for Environment, Energy, and Natural Resource Governance. She received her Bachelor of Engineering in Building Environment and Energy Systems in China, and a PhD at in the Environmental Geography Department at Peking University, with a former PhD student of mine, actually my second PhD student, Dr. Chunfeng Liu. Her research focuses on technology innovation, climate change policies, and co-mitigation of climate change and air pollution. She was cited from 2020 to 2024 by Clarivate as one of their highly cited researchers. She is an AGU 2023 Global Environmental Change Early Career Awardee, and is one of 35 innovators under 35 in the Asia-Pacific region, awarded by MIT Technology Review. Professor Meng has published widely in international peer-reviewed journals, including Nature, PNAS, Nature Geoscience, Nature Energy, Nature Climate Change, and Nature Sustainability. Her papers have received various awards, including being cited in 2017 for one of the best early career articles in environmental research letters, and top 50 Nature Communications Earth and Planetary Sciences articles in 2018. Jing is serving as the chief editor of NPJ Environmental Social Sciences, as an executive editor of the Journal of Cleaner Production, and associate editor of Journal of Geophysical Research Atmospheres. Professor Meng will be visiting Princeton for the next month. She'll be sitting in my group across from my office in Robertson, and I think she would welcome conversations and potential collaborations with all of you. So please join me in welcoming Professor Jing Meng.
Yeah, I think Denise have gave a brief introduction of my background. I just want to mention I have a interdisciplinary background, a bachelor in engineering and a PhD degree in environmental geography. So it's an interdisciplinary background between engineering and also natural science. And I moved to the UK in 2016 and working on the decarbonization pathway for the European countries in a Horizon Europe project, and have been yourself for 6 years. So the fundamental motivation of my research is a challenge of the urgent challenge of climate change, confirmed by the most recent IPCC report. And the red figure here shows the annual rapid increase in the annual carbon emissions driven by especially in the past decade, driven by the emerging economy like China and India. So the question for my research is what we can do to achieve net zero emissions. So before we can cut emissions, we need to have better data about where the carbon emissions come from. So the biggest challenge is we don't have a good available carbon emissions data with transparent source with consistent structure. So the carbon emissions across regions and across different scales are not normally comparable and good to be verified. And so the first challenge we have is how to build the accurate and complete carbon emissions. So my group starts with carbon emissions inventory with three pillars. We do lots of data pre-processing to integrate different data sources like the international and national statistic data, and also we have multiple sources like some data, especially the plant level data, original data from some commercial database. And so we constructed a structured and consistent carbon emissions inventory at multiple scale. The international, the national scale, especially focused on the emerging economies, like which is now very complete from the widely used data like IEA, and now we also construct the carbon emissions inventory for different companies, and also the carbon intensive infrastructure, especially the energy sector and also the industrial sector like steel sector, cement sector, oil refining sector. So we start with carbon emissions inventory, and now we also trying to build a economic database to identify the potential low carbon, zero carbon technologies with comprehensive analysis for the technology readiness and the historical cost, and also to forecast the future cost and the deployment with different scenarios and also policy scenarios. And the aim is to develop technology-based solutions for different regions, for different companies and the infrastructure. We have done lots of analysis built on our own emissions inventory, start from about 10 years ago. With the new build emissions inventory, we have done lots of research to analyze the historical emission trends and also the socioeconomic drivers for the carbon emissions in China, in other emerging economies, and also the air pollutants in the past few decades. For the carbon emissions inventory, we found the temporary stable emissions around 23 is driven by the industrial structure change and also the energy structure change. And also for the air pollutants in emerging economies like China and India, we found the emissions change are not only driven by the local industrial and energy structure change, but also influenced by the international consumption in other regions. And trade plays an important role in driving the global carbon emissions and also the regional carbon emissions. So the figure on the left shows emissions embodied in the international trade, especially the emissions embodied in the trade between global north and the global south increase rapidly after 2000. But after the financial crisis around 2008, the trade structure changed a lot, and also the related carbon emissions embodied in the global trade. And we found the carbon emissions embodied in the global south trade increased quite rapidly, while the emissions embodied in global south-north trade declined a bit. And due to the different carbon emissions intensity to produce the same product, for example, to produce the same laptop in the US or in China, the carbon emissions generated related to the product will be quite different. So the carbon emissions embodied or the affected by the global carbon emissions also affected by the international trade. For example, if the U.S. imported some emission-intensive products from China, it contributes to the increase of global carbon emissions because U.S. has a lower carbon emission intensity to produce the same product. So we assign the carbon emissions influenced by the global, by the international trade. And the carbon leakage is also one of the concern related to the effectiveness of the climate policy. Because the current NDC or the net zero target based on the territorial carbon emissions. So the countries can achieve carbon emissions not only through the low carbon or zero carbon clean technologies deployment, but can also outsource the production and also related carbon emissions to other countries. we assign the 2020 carbon emission target, which is from the 2009 Copenhagen conference. We assign the carbon target for 34 countries, and only 12 countries achieve their both their territorial carbon emissions target, and if we consider the carbon leakage, the carbon emissions are sourced by the international treaty, they still achieve their target. But for 7 countries, including France and Poland, these countries are on the halfway. It means they achieve their carbon targets, but part of the carbon emissions are cut by the outsourcing production activities. We have done lots of work at the national policies. So now we move to the focus from the policies to climate actions. We have acknowledged the important role of the low carbon and the zero carbon technologies for the future net zero pathway. And the future technology deployment will be driven by the macro factors like the population growth and also the GDP growth, and also the economic structure, but also constrained by the bottom-up infrastructure, like the material constraint and also the infrastructure lock-in. So the bridge between the macro factor and also the bottom-up engineer constraint is the S-curve of the technology. So we propose a multi-scale integrate assessment model to integrate the top-down model like the GCAM model, CG model, with the bottom-up information. It's the central part of our European Horizon program, joint funded with the Chinese Ministry of Science and Technology, running for it's a 4-year program. So in the integrated program, the innovative points is we have 2 innovative models. One is we integrate thousands of infrastructure information, like the infrastructure information in energy sector, and for energy emission-intensive sectors, we integrated the plant level information, the existing technology, location, age, and also the future retrofit cycle. And also we have identified the potential mitigation technologies for these emission-intensive sectors. So we have a techno-economic module. And also this will integrate a top-down module, which we include more than 200 economists. It's also part of another project, multi-regional input model. So building in this new framework, we have done lots of work in these emission-intensive sectors. So I will introduce the 3 case studies we have done to integrate the top-down model with the bottom-up infrastructure information. The first study we have finished is for the technological decarbonization pathway in the steel sector. We start with plant level database. We have 2 plant level database. One is a plant level technical database. We have production capacity and also the existing technology, location, age, and also other information related to the technology for global about 5,000 plants. And also we have another database, plant level cost database, we have the production cost for unit product in each of the plant, and also the cost structure, the cost from the raw materials, the cost from the electricity. By combining these two databases, so we have very detailed information for the existing infrastructure. And we also have a decarbonization technology module. We have about 20 potential technologies. By integrating these two different types of database, we develop a plant level net zero pathway for steel sector. For the technological module, we do extensive literature review for the historical data and also the potential future deployment and also future required deployment by standard Prisma analysis to collect the cost structure, to collect the historical learning curve, and we use the Moore's law with the forecast deployment to forecast the future cost. It's our one of the most important database we have, the production cost. It's the plant level cost data. We can say the variations in the production cost, not only between technology types. For example, the BF, BOF technology, the cost is much lower than EAF, and we can also say the variations for the same technology across regions, because the price of the local raw materials are different, and also the energy price are different. So we can say a large historical cost variations for the current production costs and also for the potential costs. So that's why we want to develop a plant level decarbonization pathway, because we can say the large variations in production technology, in the potential production costs, and also for the potential feasible technologies. With extensive literature review, we identify the historical costs for different types of technology, and we also do cost forecast with learning curve, the Moore's law, and we also adjust the technology costs with the existing cost variations. For example, the different renewable energy price and also the materials price for the future mitigation cost. With these two database, we develop a workflow for the design of the decarbonization pathway. For example, we designed the retrofit cycle for the steel plants is 20 years. Of course, we do sensitivity analysis for this parameter, and also with technology readiness, and also the potential policies in this sector, and also the future demand for the steel products. So it's all the constraints. And for the future cost, for the plant level cost, we have the different mitigation costs. So for each plant, once it enters the retrofit cycle, we identify potential available technology costs. Because of the different readiness, not all the technology are available at the same time. So we assign available technologies when the plant is ready to retrofit. And we assume the plant will choose the least cost technology for the retrofit. So we can say for the selected BF, BOF plants, even for the same technology, the potential decarbonization pathway and also the potential costs are quite different. For example, for the red lights for a typical BF, BOF plant in the UK, it has run for 8 years. So considering the different cost of the technologies, it will choose BF plus CCS, but for the India steel plants, it's also 8 years. The retrofit technology will be quite different. It will lever the energy efficiency first to improve the energy efficiency because it's relatively low cost. So with this framework, we can design plant level and actionable decarbonization pathway for specific plant. If we aggregate the plant level information, we can get the sector level decarbonization pathway. Because we consider the specific plant will always choose the least cost pathway. So we also need the policy regulation to force a plant to choose low carbon or zero carbon technology. Otherwise, it will always choose the most choose the most cheap technology. So it will neither deploy the low carbon or zero carbon technologies. So we consider 3 scenarios: early scenario, medium scenario, and late scenario. For the early scenario, all the plants will choose zero carbon technologies when they have the first retrofit cycle. And for the medium scenario, we assume the steel plants can still choose low carbon technologies. For example, they can improve the energy efficiency with lower cost, and in the second retrofit cycle, they have to choose zero carbon technology. It will enable the plants to use transition technologies. And for the late scenario, we will assume for the first retrofit cycle, there is no regulation or policy enforcement to choose the zero carbon technology. But for the second retrofit cycle, to achieve the net zero target, they have to use the zero technology before 2050 or 2060, the last retrofit cycle ahead the target year. So for different scenarios, we can say the mitigation potential and also the cost from different types of technologies varies largely. For the medium scenario, we can say the scrap EAF will play a very important role. But for the early, if we force all the steel plants to adopt the zero carbon technology, we will have to use CCS or hydrogen related technology very early with very expensive cost, more than 100 per ton carbon emissions. So the conclusion is for these 3 scenarios, if the for the actionable perspective, the medium scenario to use energy efficiency and also scrap in the short term to improve the energy efficiency and use to improve the circularity of the materials, and then move to the zero carbon technologies will be most cost effective for most of the plants. But for the overall design of the framework, we can have the plant level specific pathway for each plant. We also do another case for the oil refining industry and also primary chemical industry. We'll take oil refining industry for example. We can say the carbon emissions for this sector is very concentrated. The 80% of carbon emissions from top 20 countries, and for the company level, over more than half of the carbon emissions from the top 20 companies is only 4% of all the companies contribute over 50 carbon emissions. And we also develop carbon emissions inventory for the plant level. So it's a consistent carbon emissions inventory verified by the top-down emissions inventory at regional level, and also bottom-up plant level emissions inventory. And once we identify the carbon emission source, we also do the technology identification stage. So we identify the potential carbon emissions strategy for energy efficiency improvement technologies, and also 9 decarbonization technology, including biomass substitution, CCS, and clean hydrogen. And we also analyze how each of these technology can be compatible with other technology, because the technologies focus on different process along the production process. So we analyze the technology readiness, and also whether or how they can be compatible with each other to decarbonize all the process. We also do extensive literature review to identify the historical technology deployment and also the cost, and we analyze the learning rate, and also to forecast the potential technology cost in the future. We use the same decision principle to let each of the like the refinery to choose the least cost decarbonization pathway with bottom-up information at the plant level, and also the top-down economic level parameters like the future demand, and also the international trade, and also the industrial and the economic structure. And we design 4 scenarios with different focus. And for the one scenario focus on CCS and the clean hydrogen, and the other 2 scenarios focus on biomass, and with different deployment rate. And the principle is we also promote energy efficiency related technologies in the short term before 2030 for the first retrofit cycle, and also for the long-term deployment, we promote the zero carbon technologies. So we can say for different we also do the selected decarbonization pathway analysis. We can say for different types of the oil refineries. For example, for the first, then for the deep hydrocracking, we can say the CCS, the biomass related technology will play an important role than the deep coking plant level technology. And for the different types of decarbonization pathway, the related investment are quite different. For the accelerated deployment with bio-related material, the total investment cost can be double of that for the CCS and the clean technology. So it's our case study for the oil refining sector. And for the energy sector, we didn't focus on the decarbonization for the entire energy sector. We focus on the existing coal-fired power plants. We have built an inventory for about 9,000 coal-fired generating units worldwide, and also including details on the existing combustion technology, and also capacity, age, and location. We want to say the maximum technical details to improve the energy efficiency, because in COP28, one of the one of the great agreement is about to double the energy efficiency in the energy sector, and also to increase the related strategies to improve the energy efficiency in energy sector and also industrial sector. And for the IEA report, also for the APS scenario, one of the results is about the required contributions from the energy efficiency improvement. So we want to identify the maximum potential from the energy efficiency in power sector from the technical details. So we map the current plant level efficiency for all the power plants, and we can say the global average efficiency is 32, but we can say large variations across regions and also across plants. And we also have very detailed information for different types of combustion technology. So we can say the average efficiency for the ultra critical efficiency is higher, is 40%. But the technical details to improve the energy efficiency are quite different across types of technologies. And we also select the power plants across regions. We can say the capacity and also the steam pressure and also the reheat temperature are also quite different across coal-fired plants. So we integrate the real parameters and the energy efficiency potential from some case studies to identify the energy efficiency improvement potential from different types of measures, like to improve the fuel type, to improve the boiler type, and also the to upgrade the capacity or to change the steam flow. So we have 7 types of efficiency improvement measures, and we assess the technical potential from for the existing power plants, the existing infrastructure. So it's not the roadmap for this coal power plants. It's just the maximum technical potential. So we do the assessment for each of the 9,000 coal power plants and assess the improved potential. And also we aggregate the potential, the global improved potential, and we can say the potential efficiency improvement can only contribute to about 30 gigatons, so constrained by the technical potential. But in the real world, due to the feasibility of the improvement measures, because some of the measures can also be very expensive, like the fuel type change can also be very expensive. So, but even with the maximum technical potential, it can only contribute to less than 1/3 of the required carbon emissions from the IEA assessment. So it means in the long term, the contributions from the energy efficiency improvement can be very limited. So we still need to deploy more zero carbon and other low carbon technologies like CCS and hydrogen. We have submitted this paper, and now it's in the revision stage to improve the scenario design. It's all my talk, and I also want to introduce this new journal. It's quite interdisciplinary journal. I think the topics are quite relevant to you today. It's about environmental economics, and also we promote interdisciplinary study to use more disseminate methods to address the current environmental challenges. And we have different types of contents like articles, reviews, and perspective, and other new types like protocols for maybe some software and also database construction. Thank you. Ready to take any questions?
So thank you so much for the detailed analysis on various industries. The floor is open to questions.
Thank you. Could you comment on the role of electrification in decarbonizing various sectors that you've been researching?
Sorry, can you speak?
Decarbonization.
Or electrification?
I'm sorry, electrification in decarbonization.
Electrification.
Yeah.
Yes, we for the industrial sectors, all the sectors we focus are very hard to abate sectors. So we consider the potential electrification pathway because when we consider the economic cost, we consider the cost from the electricities. So it's we consider the electrification and also the potential cost integrated in our different types of technologies, but we didn't consider electrification as a separate way to decarbonize these plants.
Maybe I can ask a follow-on question regarding your coal power plant analysis. It seems like you're including CCS as a mitigation option that would lead to reduction in your CO2 emissions, but that I'm wondering, like, there's still a huge gap.
Yes.
And does it make sense to implement some of these technologies? CCS might be really expensive. It might not be feasible in all places. What about going directly to non-fossil technologies instead of improving some of these really old, inefficient coal-fired power plants?
So in this paper, our detailed analysis is about 80% of the analysis focusing on the potential contribution from the energy efficiency measures, and then we aggregate all the potentials from the plant level and to compare with the required decarbonization pathway in different SSP scenario. So it's we didn't analyze the potential contribution from CCS and other mitigation technology. We just want to say energy efficiency is not sufficient to mitigate. And now I think it's also relevant to the comments we got from the reviewers about the feasibility and also the it's like because one reviewer said I think his understanding is like we promote energy efficiency as an important strategy, and we are disencouraging the deployment of CCS and hydrogen. Now we are changing the narrative and want to analyze more scenarios about how we can integrate energy efficiency in the short term and also the CCS and other renewable energies in the long term to achieve the net zero target. Because our primary objective is not to design decarbonization pathway for power sector, but it seems the reviewers are quite confusing about why we focus on only energy efficiency part. Yeah, so we are now working on the revision stage for this paper to add more analysis to improve the scenario analysis to integrate the role of CCS.
The amazing amount of data, and I wonder when you talk about reviews, how do you approach these industries, and in their responses, do they think about accelerating, like changing their industry, basically close or shut them down and move them into something that's renewable type of energy? So I don't know. Obviously, here in the U.S., there's this huge resistance to do that, but what's the reaction you're kind of seeing from companies in terms of where they're going to be?
So for the for the two case study for the oil refining sector and the steel sector, we didn't approach industry experts directly, but we integrated the expert elicitation for the future deployment of the technologies. So for the CCS and the hydrogen technology, we integrated the expert elicitations for the potential, the readiness, the available year, and also the trend of the future cost. But we didn't approach industry expert directly and integrated their their decisions into plant level decarbonization pathway. But we want to say how we can provide scientific evidence by integrating the national level decarbonization, the national level targets to provide scientific evidence. But yeah, to integrate the real, not only the decisions from the industry expert, but also the maybe most up-to-date data from the plant level is our next step, because now we heavily rely on the data from the third party, the commercial database. Sometimes maybe quite out of date, or it's a bit different from the real world data.
I have a similar question, but maybe I can ask in a slightly different way, which is more about the method. I think it's absolutely important to start with the least cost pathway, because that's always the first pass if we can achieve it. I wonder, in your framework, have you thought about incorporating other priorities? For example, what if once you started thinking about social, political, and institutional feasibility, are there like other pathways that are actually more realistic, but probably a little bit more costly?
Yeah, I mean, we have to, now we consider the economic cost will be the only factor which affect the decision. But for the overall framework we develop, we want to integrate more not only social factor or political factor, but also other relevant the co-benefits or trade-offs. Yeah, I think we have to integrate this in the future, but now for the first step, the model we only consider, because we consider in the real world, because the current top-down models, the optimization based on the aggregated cost at the national level, we think it's far from the real world, because for the companies or for the plants, the owners won't consider the aggregated risk cost. So we just move from the aggregate cost to the plant level cost for them to make decisions. But next step, we will integrate more modules like health modules and other land use and biodiversity.
In your plant level analysis, I had two questions. One is, when you do retrofits, what do you look at individual sites to see what the feasibility is of actually putting in a CCS unit, for example? That's one question. And the other is on the, anytime I've worked with plant level data, there's always concerns about confidentiality and exposing commercial secrets or whatever. Are you able to publish your plant level results and such that people could actually identify specific facilities that you're modeling and so on?
Maybe I can answer the data question first. So we're asked to make all the data available when we submitted the one of the paper will be online next week. But when we publish all the original data and also the results, we mask the real name of the plants. We only give the plant number, 1, 2, 3, like this. And it's also restricted by the license. We cannot, because we about some of the data from commercial database, we cannot publish all the original data. It's not only about privacy, but also by the license restriction. So for the first question about the plant level deployment of CCS technology.
Well, retrofits more generally. Is there room at a plant site to put in a unit that you assume is going to be put in?
So for the retrofit, we consider all the deployment of technologies like retrofit. Not only CCS, but other like the energy, not energy efficiency. Energy efficiencies we consider they can be improved maybe immediately in the short term. But when we consider the retrofit, we have identified all the maybe for the steel sector, we have about 120 technologies, and for oil refining, we have 9 technologies. We consider all the deployment of different types of technologies as a retrofit.
So just following up on that, how frequently do you find that CCS is a viable option? Because installing CCS will always increase the cost. How frequently does that come in as the lowest cost option in your analysis?
We consider the readiness as to decide whether this technology is available or not. And for the cost, we forecast the cost for all the technologies, and we compare the cost of different technologies when all of the technologies are available.
So how frequently is CCS a choice that's adopted according to your analysis?
How frequency?
Like, is it 10% or is it of the technological options you're analyzing? Because one concern I've had always with CCS is that it always adds to the cost.
Yes, yeah.
And it's not necessarily feasible because of the subsurface geology and the piping that's required, and it's a challenging implementation process. It's expensive. It's always an additional.
Yes,
efficiency will improve your cost effectiveness. CCS
for the CCS we consider it's only available after 2030, and for the cost we collect the data from the industrial reports and all the literature to decide their future learning, not learning rate, but their future deployment rate, and also integrate the potential capacity from the scenarios, so we can draw a line about the future deployment curve.
How often do you have an estimate of what's the best technological options, cost effectiveness, and
cost effectiveness? The technology for the CCS, we also consider the electricity cost. So for the plants for the steel plants in India, scrap is quite a cheap option. So scrap is quite popular, and for CCS, I think for most of the European, I can't remember the number, but for most of the European steel plants, CCS is quite valuable because we also consider the carbon price.
Oh, the carbon price.
Yes.
That would be a big driver.
Oh.
Okay, thanks. Other questions?
One more question. I think, can you go back to the previous slide, the one you showed the modeling framework, the top down? Maybe the previous, I think there was one, yes, this one. I think it's very important to thinking about, a couple of models across scales. I think that's absolutely important, but I'm just curious, also as someone who has been thinking about this, when we couple stuff into this, how can we also make sure that we understand what is happening there, and how can we ensure this model is still tractable, and how we really thinking about how the uncertainty may propagate throughout the system so that we actually have an understanding of the robustness of the ultimate outcome coming out from the model.
Yes, for this framework, we want to improve the motivation for this framework is we want we can say for the current AM model, they consider only aggregated costs, so they cannot provide insights into the granular level. And also for the technology representative, we have only limited numbers of technologies, only less than 20 technologies. So we want to improve this to integrate the bottom-up information. we are trying to make the relevant parameters as consistent as possible. For example, for the steel sector, and we have the output from the steel plants. So we make maybe the total output from all the steel plants from the bottom-up information and the top-down information consistent. And for the carbon emissions, the IAM model or the CG model, they also have a carbon emissions data from their default value, and we also make the number consistent. So we are trying to make all the numbers, the linkage between models are consistent. But for the potential uncertainty after integration,
It's really hard, that's why.
yeah.
About this question as well.
Yeah, I think it's quite important question, but we haven't do the uncertainty analysis or the potential uncertainty from the integration to maybe compare the original model. Yeah, we haven't do this already, but maybe we can consider how to improve this. Yeah.
Okay, great. Well, if there's no more questions right now, Jing Meng will be here for another few weeks, and I think we look forward to continuing the conversation.
Thank you.